Yes, let's go. Günaydınlar, herkese hoş geldiniz. Zaman ayırdığınız için teşekkür ederiz. Bugün Cadence AWR'ın güzel, ilginç bir sunumunu dinleyeceğiz hep birlikte. Ben Neslihan, Aktif Neser'den. Hepinize güzel bir webinar diliyorum. Sunumu Andy yapacak bugün bizim için. Andy, stage is yours.
Thank you very much. Hello and welcome to our webinar. Thank you for joining us today. We'll spend about the next 50 minutes or so going through some slide material, but also as I'm an ex-engineer, I'll try to show the software running alongside the presentation. Live webinars and demonstrations are always exciting, so we'll see how we get on today. My screen for the demonstration is to my left, so I apologize if I look sideways. A quick bit of background about myself, just so you know who I am or where I'm based. I'm Andy Wallace. I've been working with AWR software for over 25 years now, having come from that team previously as part of the UK and European technical manager. My role when we were acquired by Cadence in 2020 is to look after, continuing to look after the AWR microwave office and VSS tools, but alongside that, the PCB packages, Allegro, our signal integrity packages under the name Sigrity, and that Sigrity package contains 3D FEM solvers Clarity, but also thermal tools called Celsius. And we'll be touching a bit on Clarity as a 3D solver with our phased array webinar today. Just at the top of this slide is my email contact address if you wish to get in touch with me directly. But please do go via Active Nessa, Leslie Hannon, Mert and the team with any questions you may have. I'm hoping that our question and answer tab section is open for live questions as we go through the webinar today, but that doesn't always run smoothly. And if you prefer to ask private questions, please drop them into an email to us. Today we have a busy slide deck. We'll look at trends for driving antenna array design in particular, but it's a vehicle for us to explain the simulation software from Cadence, in particular Microwave Office, the circuit and frequency domain tool, VSS, the visual system simulator, and in particular for this application, the EM simulation tools, Axiom, Analyst and Clarity, and we'll define those as we go. We'll look at the antenna array specifications and the RF planning for that type of design, and start very simple with a single element. The example slide deck has got quite a complicated multi-layer PCB board design, and we'll look at that. But I'll show the examples with something straightforward. Going on from there, we'll look at the phased array generator wizard that's within inside Microwave Office, integrated feed and front end components producing a final PCB, and how we can look to route that. Now, the slide deck will be made available after the event, so if you have questions there, they can be shared after the event. Hopefully they will come from Active Nessa if you're happy to provide your email. This video or webinar is being recorded and the video will be reviewable also. Now, just as a quick reminder, Cadence do have a stand at the European Microwave Show in a couple of weeks. This is the 21st to 26th of September, running in Utrecht in Europe, up in the Netherlands. Please do come along if you're attending to see our business unit heads. That's the guys that run the electromagnetic team, the people that run the AWR and Cadence systems business unit, and ask your questions to those directly. Sadly, I will not be attending this year. So let's look then at a quick introduction on the trends generating and driving our phased array devices today. Of course, we're always pushing for greater and higher system performance, almost always at lower cost, reduced size and weight. This type of technology is being driven not just by mobile communications, the likes of cell phone handsets, but also microstations in buildings and in highly urbanized areas. But of course, also the vehicle-to-vehicle communications, things like anti-collision avoidance radar, adaptive cruise control. And all of these types of designs require advanced packaging, and in particular the RFIC, the RF integrated circuit, and the monolithic microwave integrated circuits to be integrated together in an overall design, to be shrunk in size. And those to work in the phased array technology world. Quite often I'm referring to electronic steerable antennas. We need to consider how we analyze those and the design flow that is appropriate for these to produce those physical designs, and to look at those physical designs and how they interact and perform once assembled and fully manufactured. And of course, what we're proposing today is the design analysis and workflows available to you from Cadence today. Right now, the integration of Microwave Office, that's the AWR tool set along with VSS, is part and parcel of the Cadence design suite. Virtuoso is for the silicon design at silicon chip level, quite often required for high integration for advanced node designs, be it memory or digits control. And Allegro, the PCB tools, is another platform that Cadence provide for RF microwave PCB layout, but also low frequency and power designs. And what we have today is an integration between all of those three tools working very, very nicely together. That gives us the ability across all of the technical verticals, be it mobile communications, aerospace and defense, for example, to look at designing the digital, the analog and the RF circuitry, to be very process aware on the type of board technology, be that gallium arsenide, perhaps for higher power designs, right through to PCB stacks, maybe on FR4, to consider that IC and advanced packaging, but also the routing around the board. It's technology independent. It's appropriate to use the correct technology for the correct requirement. I've mentioned gallium nitride there for high power, high frequency transmit chains, but also your very exotic laminates and multi-layer boards for high integration. And of course, perhaps the silicon devices for including the processors, the memory, the digits control. And it's critical when we pull all of these elements together that we have the ability to run through electromagnetic simulation in the design flow. And we can use that for optimization of parts of the schematic or the design or the layout, and make sure that we're getting the best from the approach that we're taking. That EM analysis can be provided across the chip package and board. And indeed, although not covered in this webinar today, we can also offer thermal analysis with the Celsius tool that I mentioned earlier on, fully integrated into the design flow. So you would simply take the board design and throw it out to the 3D electromagnetic or 3D thermal tools automatically without any export and import of files. Here's a preview of the final board that we'll be looking to produce and is used as our vehicle today for analysis. It's on a very large stack of material. This is the PCB stack of material that you can see there. Multi-layer printed circuit board. In fact, there's even an air gap, and we'll explain why that's included in the stack as we talk about the single antenna. It's an aperture coupled stack patch antenna sitting above all of the digits control and the surface mount components underneath. These are live pictures that you would have seen come from Microwave Office as a top level 4x4 patch array in the top left corner, and the control electronics on the bottom left hand corner of the board underneath. And in particular, we want to look at the phased array radiation patterns from this design, not just in the ideal world with the patches at the top left corner, but with the interfering electronic components sitting under the board, and with the interconnect tracks, ground planes, and other problems that we might introduce because of the integration of all of these into one design. In terms of the development workflow, one could start in one of two ways. Quite often, if you're designing from scratch, you'll start with budget analysis, and that's where VSS, the Visual Systems Simulator, sits. This is part of the AWR design environment, and allows us to do budget analysis, component selection and system architecture, looking at aligning the proposed system diagram and communications link going forward from there. It's in this tool that we do the phased array antenna synthesis, but that is synthesis. That is looking at the ideal performance of a perfect design without any of the degradation of the PCB board sitting underneath. We can then take that flow into the EM world, and either with planar tools or with true 3D FEM tools. Planar is Axiom, 3D is Clarity and Analyst, and I mentioned a moment ago we could even do thermal analysis too, and look at the physical chips, the bond wires, the board stack and the solder balls, for example, in this lower picture, and look at the radiation patterns and the degradation in radiation going forward, and take that acceptable design and make a finished final layout using the tool to look at integrating surface mount components, the interconnect and the overall performance of this board design. That's the flow one would take if you were designing from scratch, moving from left to right. And we certainly have an idea within Cadence that you shift left, you do more of this analysis up front before manufacturing the board, so that problems are found early on, resolved before manufacturing prototypes are produced, and you're able to design faster, in less time to market, and at lower cost than you might otherwise take if you make multiple prototypes and have to redesign those by finding the problems later on in the design flow. Of course, there are customers that have already have those designs, and we can import printed circuit board layout as ODB++, as IPC 2581, or as Gerber files. We can bring that into the design world. We can reverse engineer and analyze the electromagnetic performance, and we can reverse engineer the system performance back into VSS. The beauty of the tools that I'm proposing today is that you can work left to right for design or right to left for analysis. It works in both situations. There are multiple design and analysis stages behind the development of quite a complex antenna array, getting to the point of PCB or package integration and those front-end RF electronics. But the flow that we're presenting today would start with the specification, the geometry and material definition, and the simulation and optimization of the proposed antenna array. We then take that concept and look to stack that, the phased array wizard. This helps us to determine the number of elements, the orientation of those elements, whether we need to use a thing called gain tapering, adjusting mathematically the power transmitted to each of those elements dependent upon their position, and look at the far field analysis and beam angle steering of this design. We then need to integrate that into the product and make sure that we include not just the ideal feeds, but real parameterized components, maybe the steering components, the surface mount devices that will do the electronic control, and build this up to a final PCB board that we can physically produce. We're including there the component placement, perhaps S-parameter files from the devices that we've imported, certainly manufacturing devices that we can physically pick off the shelf and use going forward. We'll talk about more of those individually as we go through the slide deck. So if we look at the tools provided by Cadence today, I've mentioned those on the left-hand side, the system planning tool, VSS, within mmWave Office, the material definition, the circuit level analysis, the parametric antenna design in the EM world, and the phased array generator. But of course, we do have Virtuoso for the silicon chip design. We can pull upon those silicon designs with a product called Virtuoso Studio RF and bring that silicon intellectual property, silicon IP, into the mmWave Office tool. So for example, if you were doing a beam steering IC, that could be included in the simulation at circuit level. And we can push those tools over into our PCB platform. That's Allegro or Allegro X today. That also includes the Advanced Package Designer, APD, in order to continue the PCB design if it requires more digits design, more power or low frequency design over and above the RF sections. And of course, clarity, the 3D EM tool, works with the whole flow. Doesn't matter whether the circuit level was designed in microwave office, in the EM tools within inside the microwave office tool, or whether designed in Allegro and taken into account the full board. So let's get on with our system specification then. Back of an envelope calculations, we refer to this in the UK here as a way of estimating the design in a very simple form and format. The table on the right is what we're going to talk to in just a moment, but we're looking at the receiver sensitivity, the signal to noise requirements, and in particular the path loss over something like a 200-meter link. I appreciate this is not massive distance, but it's just the vehicle to explain this particular design platform. We're always limited on Earth with thermal background noise. Minus 174 dBm is the minimum you're going to get here, unless you go up into to space, perhaps. And we add to that the bandwidth of the signal that we're working on. We're working on a 200 megahertz signal here, and this is up at 28 gigahertz. So we have our base thermal noise floor of minus 85 dBm. 850 megahertz bandwidth at 28 gigahertz that we're sitting at. This is the lowest power level that we would expect to operate in the system here based on Earth. We're giving ourselves a 6 dB offset for the noise figure, taking our noise floor to minus 79 dBm, and a signal to noise ratio of 4 dBs before the antenna. That gives us a minimum received power of minus 75 dBm. This is dBs in milliwatts received at the receiver that we're able to have an operating link. If we look at the effective isotropic radiated power, we need to add those parameters together, and we end up with a radiated power required of plus 60 dBm. That's taking into account our massive 135 dBs line of sight path loss, and that's what we expect to be including just here. The radiated power, in order to hit that, we're assuming to be about 2 watts from our transmitter at 33 dBm. And that therefore gives us a requirement in the antenna gain for 27 dBm. Now, I am aware that there are some hands being raised in the audience. I don't know if I'm able to get to the questions whilst presenting, so I will try to pick those up towards the end of the presentation. Please do continue to ask your questions in the question and answer box in the Zoom control. So I mentioned VSS, the systems block diagram tool. That's where we start looking at this. And if you didn't want to do back of the envelope calculations, you're able to put these figures into our system simulator tool. So for example, here you will see, when I advance the slide, that we have our 135 dB massive path loss as the path loss. We're assuming line of sight, but the model itself can look at multipath bouncing, perhaps from the ground or from atmospheric reflections. We have the transmit power of 33 dBm coming from our transmit amplifier, and the proposed gain here of the antenna of 27 dBs. That's what we're hoping to get from our phased array antenna design. That will be clearly dependent upon the number of elements, the spacing, and so forth. We've also been asked about the data rate. At the moment, I'm assuming CW signal, but we will look at one of the final slides, looking at a 5G live test signal going through this design, and the data rate would be set there. We've got some receive antenna gain in our receiving unit, and looking at the link budget analysis, we can propose that that link would work, assuming that we had 27 dBs gain from our antenna. That's our magic number, and that's what we're going to work towards with the proposal for our phased array structure. Now, within VSS, we don't need to use a single transmit antenna with ideal antenna gain. We could in fact import measurement data files. This is phi and theta, a measured angle into an antenna model, and sweep that. That's the one that we have on the right. Or we could have just an antenna radiation pattern that we can import and use that directly. These are behavioral models still in the VSS tool, but they're still relatively ideal. They're isolated antennas that are behaving themselves. What I'm going to propose in this webinar today is that we use the phased array wizard. This sits under the wizards branch in the project tree of the mmWave Office software, the AWR tools. And in that phased array wizard, we have various tabs that we set through. We step through those and look at the array control and general setup, the array geometry. And what we do today will be a lattice on grid, on a square or rectangular grid design, but it does not have to be that way. It could be circular. We could have custom coordinates for the arrays. And we can also look at producing gain tapers. There are normally three generic gain taper approximations that are used in phased array work. Obviously, uniform is the same power to every patch, but we have the Dolf-Chebyshev approximation or the Taylor approximation, where as we get closer to the antenna elements on the edge of the array, we start to reduce their power levels to help shape the beam. Again, you'll see some of that in future slides. Within the phased array wizard, we can even look at array imperfections and start to damage or disconnect some of those, either intentionally or random, to look at element failure and the beam shape when we're undergoing failures in the design. The tabs allow us to set up, as mentioned, the lattice, the antenna gain for the individual antennas. And in our example here, we're going to set that to around about 5 dB per patch and have the multiple array elements multiply up and give us an overall antenna gain of 27 dB for hitting that budget analysis that we've mentioned a moment ago. The recommended amplification level, we have a question just now for the chain can be input here. We have the ability to add that, and you'll see in a moment that we're working on 33 dBs drive power. That's 2 watts coming from the transmitter. So if you've never seen mmWave Office or AWR design environment before, I've got a screenshot here. Remember that the slides will be shared. You can get access to these, and after the event, either contact Active Nessa for a trial, or by all means get in touch with me to run through these steps. The PDF that I'll share will not have this live video, but there is a live video here for our webinar that I can play while we're talking, and hopefully you'll see that advance through. We click on the phased array generator wizard. We go through the analysis setup, and we propose the transmit and receive frequencies in here. You can see that we have the ability to look at importing antenna radiation patterns too. But more important at this stage, we're proposing a layout topology, and this is a 2x2. There is our individual antenna gain that we're proposing we can achieve per patch, and at the moment it's set to 5 dBs. You'll see the single patch design in a moment as to how we achieve that. Now we can go through that geometry, and as a 2x2, i.e. a 4-element array, we can look at the proposed synthesized radiation pattern, sweep frequency, and make sure that we're getting the expected radiation gain. You can see it's very light here at 21 dBs. It's not enough with a 4x4 patch, sorry, a 2x2 patch, a 4-element. So we increase that. We take that perhaps to a 4x2 or maybe even a 4x4 patch in order to achieve that overall transmit gain. You can see here that we can play around with the tapers in the synthesis tool and certainly focus that power on bore site, and you can see the antenna gain increasing as we do so, to the point that when we get to a 4x4 or 4x8 array, we are within our 27 dB gain requirement. So that video there was to show you, but I'll show you in the software as well in just a few moments. We're assuming an antenna individual patch gain of 5 dBs for this example, and that when we array that across, we get more than 27 dBs, in this case, ultimately relying on a 32 element of 4x8 array patch if we include gain tapering. Advancing through then, how do we do this design work, and how do we go about physically doing the elements? For the paper, this webinar, we're basing the individual patch antenna on a particular design that's proposed by this gentleman here, David Poser, back in 1985. It's the idea of a slot-fed antenna. So at the bottom of our board stack here, we have our drive line. We have a ground plane with open slot to help focus. We have a focus patch on one layer, and kind of it's actually to enhance the bandwidth, a second focus patch on a second layer above, but with air between the layers. It's quite a complicated stack of material. We can scale that to operate at 28 gigahertz, and we can use the it's actually a tool to help us set up the board stack of material that you'll see in just a moment. Now, on the live example that I'll show you in the software, I'm not going to be designing this one from scratch. There's too many variables to get wrong in a live demonstration, but I will show you a single patch antenna and how we set this up. So in the real design, we have a multi-layer, multi-PCB stack of material. Here you can see cross-section of the feed line coming from our surface mount devices on the bottom side of the PCB board, a gallium nitride amplifier, beamforming chips all controlling the beam power and direction, feeding through to an element here that is effectively our transmission feed line, feeding through that slot that I mentioned in the ground plane, our bottom patch, an air gap, and our top focus patch. Now this is on our stack of board material you can see here. And what I've done in the actual project is I've set as a variable the air height and the height of this last substrate layer, so that we can optimize those. They've been set to H1 and H2, and indeed we've got a large air gap behind the bottom side of the board. So it's important to get those right and include those. There is, as I mentioned, under the tools menu, a create new process, and that allows us to go in and set up the PCB stack of material. We simply go into the software, we start this new process wizard, we define the number of layers. Sorry, it's quite small here, as perhaps an 8 or a 10 or a 15 layer board. We explain and set the various permittivity layers. So you can see here I've made my air gap, and indeed we can actually optimize some of these layers inside the tool. That wizard will generate all of the interleaving via models, both as a solid through via, but also all of the independent via lines that go between layers, and give us the option to choose those in what we call the process design kit. That really is for another webinar, another day in terms of its own setup. If we come down, we've got a small video here talking through again how that's done. So we go in and specify the parameters that I've mentioned. Those parameters can be set from the create new process. You'll see it here, and we can change the permittivity of certain layers. We can add metal conductors as ground plane or not, as the case might be, and define those via holes as we go. So that is our starting point for the PCB stack within inside mmWave Office. That gives us the ability to use all of that technology board stack as proposed by the original single element antenna array design. Now, of course, Cadence do have PCB tools. Allegro is our PCB package, and we can, of course, interface into that by reading in the unified libraries from Allegro. Having exported the technology file, we could bring in the board stack of material from Allegro directly into the PCB tool. That allows us to design with inside mmWave Office based on a printed circuit board stack of material, the properties, the thicknesses, from the Allegro tool in the first instance. So let's go on and look at the individual antenna. That's the one I've just mentioned in the paper by Poser. The idea of an upper and lower patch, the air gap, the aperture feed. What we've done here is we've put together that design in an EM structure, an electromagnetic structure. It's planar in nature, so there are layers, so we can use a method of moments tool in our product that's called Axiom. And although we've set design dimensions for the patches, you can see here on the screen that we've grabbed those elements and we've set up parameterized optimizers. These are just parameterized modifiers that allow us through the optimizer to change their values. And hopefully you can see on the right-hand picture here, that's both the length and width of the patch, but also things like the size of the slot. And on the bottom corner there, you can even see that we've optimized and set the offset center of the feed transmission line under that slot. Now in 3D view, you can see it here in the Axiom tool. We've got the layer stack of material from the Create New Process wizard. We've got on the bottom right-hand corner the optimized elements that have been set, and we've set up those parameters in the EM tool to allow us to optimize them. We have various optimizers inside Axiom, but the artificial intelligence one based around, we've called it the pointer optimizer. We'll use different methods, and we can either do multiple point sweeps and extrapolate the best answers, or we can let the optimizer hunt down the best performance. Now that's not just the case on the top of the patch, but also on that feed line on the bottom lower layer. And you can see that once we've run that optimizer, we were aiming for 5 dBs of gain from this patch. In fact, we're generating 9 dBs of gain from a single patch, more than required for our antenna array. That might mean that we can get away with a 4x4, an 8 element patch, rather than a 4x8, a 32 element patch ultimately. You can see here that we've got reasonable return loss across the band of 9.5 to 12 dBs. And these results are shown for an air gap height of that air layer of 0.76 millimeters. With the ability to speed up the electromagnetic analysis with parallel simulations. So at the moment, as that standalone design was run on one computer with one license, you're looking at around about 52 minutes to solve that with the optimizer and come up with a solution. That's running locally on one machine for the planar tool. But we can, of course, with more tokens, allow us to run multiple parallel jobs on the same compute machine. That's what we call local parallel jobs. You can see it halves the simulation time to around 36 minutes. We can run a single license on multiple machines across a compute farm type approach. We're now down to 12 minutes, 1/4 of the time. Or we can actually run multiple licenses on multiple machines, either on the cloud or on a compute farm on site, on premise. And that drops our simulation time with this planar solver, even with optimization, down to around 6 minutes on the compute farm that I had access to. This is running effectively 3 licenses over 6 machines. That's 18 licenses or 18 sets of tokens. But the solve time is an order of magnitude faster. This isn't taking very long to solve that critical problem. And we end up with a design, as you saw there, of the patch. Now that was done in a planar tool. We can, of course, copy this directly across and run this in the 3D FEM, finite element method tool, Clarity, or today Analyst in mmWave Office. And we could include things like the microvia. That is a true 3D shape. We do need to simulate that across its height. And if you had a radome or any plastic around the patch, we could include that in the 3D engine. These are things that cannot be included in the 2D method of moments or the 3D planar tool Axiom. And we can double check that the match and the drive levels of the radiation levels are correct in Clarity. And once again, having optimized those parameters, you can see here the Clarity pictures of radiation, including the via holes and the optimization goals on the left-hand side. Now, because I like demonstrating the software live, let's jump, I hope, to what you can see now is mmWave Office. Here is a planar patch antenna. It's not quite the multi-layer design. It's simply an edge-fed design. We've done this by drawing shapes. The shape modifiers that I mentioned, we simply pick up the shape and go and draw parameterized modifiers against any of those design elements. Once we've got that set up, we can simulate that. That simulation is running on my local machine while I'm sharing my design, and you can see immediately real lifetime simulation, the results from that design. If I go and view all here, you see the radiation pattern that go above a ground plane and the values here. I have set up optimization goals, so we can go through the simulate menu and into the optimization. The optimization, as I mentioned, we do have artificial intelligence under the pointer. In this case, I've got a grid search. And to give you an idea of the simulation time live on the webinar, I've hit go. We're doing multiple frequencies. I appreciate it's a slightly simpler patch, but you can see the software now hunting down the results that you see here on the screen. And what it's doing is it's changing the size of these parameters. And hopefully you can see this patch dimension changing as we go. It's now done its 5th iteration. And I asked it to stop at the best value of performance. So here it's stop at minimum error. So when we stop here, you'll see that what was off-grid in the first instance is now designed to be a nice 5 gigahertz patch. On the webinar material, we simply centered this around the 28 gigahertz frequency point. Here's the final design with its given dimensions. If I revert back to the original, you can see that there are different dimensions, and that was originally off frequency in the design that we had as I brought that in. Now, I think we had a question about actual ratios, antenna radiation pattern types. It just so happens that I've got another antenna here. This was a log spiral that was done, the imported design. And in this case, when we run the simulation, once again, live for you during the webinar, I've got that set up. Apologies because I was using multiple solvers. You can see that we can look at the radiation patterns, and those radiation patterns give us the ability to look at polarization, at transmit radiation direction, and match of this antenna. So I hope that's useful. Let's come back to the slides. We'll talk now about the phased array generator. Once you have that single patch done, what we can do is either generate a radiation pattern from that and use that as data inside the wizard itself, or we can simply go away and use that wizard. You saw a video slightly earlier on, and set up that patch array to look at the performance on the synthesis side of the tool. Now, we do have to have some thought about grating lobes, we call them, spatial alias. This is dependent upon the wavelength of the patches that are separated, but the synthesis tool gives us the ability to trial those. And it's very, very simple to drive. Let me drop back into the software. Under the wizards branch here, you see that we have the ability to go into the phased array generator wizard. That gives us the option to, although shown as squares here, I'm going to use my circular polarized log spiral antenna. Decide the number of elements. They don't have to be rectangular, as I mentioned earlier on. They could be in a circular pattern. They could be on a custom coordinate location. And whilst we're synthesizing here, having added the frequencies and other information that we need to edit, we can in this tool start to look at the radiation pattern. And that radiation pattern gives us the ability to look at the synthesized performance of this design and look at the idea of adding tapers and taper control. Could we focus that beam with mathematical approaches? Most definitely. Could we look at using a better way to focus that beam? The Taylor approximation of the way that we feed the power gives us the best concentrated power on bore site. And what about then when we steer this beam around in the synthesis world? Can we look to steer that in the X, Y, Z directions? Most definitely. And this is all under the synthesis side. But once we've finished the synthesis, we simply go into the generate menu, generate a schematic layout. This will populate this with Axiom. And if we have underneath a design that we've already generated, you saw my log spiral antenna just a moment ago, we can use that as the individual element. And the minute we finish this wizard, the software goes away, it automatically populates the Axiom 3D planar method of moments tool, generates the measurements that we require, and it comes back with effectively a final solution. Apologies, I've got some windows on the other screen just here. And you'll see that sitting under here, we have a phased array design in 3D on a 4x4 grid with our log spiral antenna. So very, very easy to drive that synthesis tool. Let's come back to our slide deck for now. Once we have our proposed antenna array, we need to go away and consider how we drive that electronically. I mentioned that we were using a 33 dB or 2-watt amplifier chip. I've gone away and I've found one of those devices, in this case from Corvo. You can see on the left-hand side here, we've got transmit small signal gain of 27 dBs. We combine that with our antenna of 5 dB gain. We get close to our 30 dB radiation that we need per patch. And that is imported either as S parameters or as a non-linear model for simulating in microwave office. We can import the package outline, and that package outline becomes part of our feed network. not an ideal amplifier in VSS, but the feed network inside mmWave Office. We can do the same with the transmit receive switches and import their Gerber outlines or ideal profiles and start to feed those together with the circuit level design, where we import the surface mount components for the electrical control of this antenna. What I'm proposing doing is in the proposed electrical schematic diagram, rather than have ideal switches as behavioral models, we're replacing them with the actual device. We're using routing inside mmWave Office, or routing between the devices, to draw our PCB tracks. We're using surface mount splitters, or perhaps drawn splitters in the topology of the board stack. And most important and critically, we're taking the feed, you can see on the bottom right corner here, to all 16 antennas and treating that as one lump of interconnect that we throw at the electromagnetic simulator. What that will do is that will pick up the coupling of those tracks, their interaction with each other, and that can also then be included in the overall design as an S parameter file, picking up the interactive coupling between each of those patches and the feed lines that are going on. So that routing and physical design, as I've mentioned, we take out to an EM tool. It would automatically put on the ports. They're no longer ideal transmission lines or strip line models in the circuit level simulation tool. They really do have material loss, roughness. They are buried inside the PCB stack. And if we have 16 of those that all couple together, we do find that there is a return loss. We can look at their phase response to make sure that we're getting the right phase, the appropriate patches. And you can see here a return loss of under minus 30 dBs across our band of interest. In this case, around the 28 gigahertz mark. We do have some loss. This is real copper. So on the right hand side there, you can see that we've got about 0.4 dBs of loss per 10 millimeter strip of the transmission line track. That means that we have to be careful how long these lines are on the control. Now, just to mention, if you were only using the system simulator VSS, we do even have interconnect models in there today within the systems tool. This can pick up the EM simulation as parameter file, and it would include the cross coupling between tracks, for example, the IF and the LO feeds, the RF output trace that might be driving into our RF amplifier chip and how that couples back to the local oscillator. And the S parameter file from that EM tool can be used purely in the system simulator. Remember, of course, that's a linear only interconnect that we're including in the simulation there. So let's move on to the simulation results. We're coming towards the top of the hour. I've spoken about the individual patch. I've spoken about some of the control electronics. Let's look at the final board as we close out this webinar before we take some questions. We've uncovered that actually with optimization, the individual patches can give us 9 dBs gain per patch. That means that rather than the 8x4 array, we can get away with a 4x4 array and still achieve our 27 dBs gain from the overall design. Those are put together as circuit level schematic elements with all the electronics control. As you can see, these are now pictures from within mmWave Office that I'll show in a moment. And that resultant array is thrown at the electromagnetic engine. In this case, this is the planar tool Axiom. And what we're doing here on the top right corner is we're looking at the 4x4 array standalone. That's without the electronics and the feed transmission lines, the surface mount components on the bottom side of the board. And you can see it's very close to the synthesized radiation pattern. We have a very, very focused beam on bore site, directly away from the element, with very small side lobes. When you start to introduce and include the plastic parasitics from the devices underneath, the transmission lines interconnecting those electronics, and the beam steer issues that you have in terms of the control and power planes, the active electronically steerable antenna, the ACER antenna, 4x4 module in the center there, starts to have a lot more detailed side lobes, this side radiation power, and that can become dangerous. We need to look at a way to reduce that, potentially either through filtering or a way of controlling that, assuming it's unacceptable. It might be that these power levels are so small that we can get away with those. Now, again, I'm an ex-engineer. I worked at Marconi for 10 years designing electronics, and in every webinar that I run, I like to show the software itself. So what I'm going to do is jump into an example here. This example is taking a very simple single element array patch that you saw a moment ago. This was the feed one that I had. In this case, not fed from the edge of the board, but fed from a port in the center as a coax feed underneath the PCB board. What I've done is I've used the phased array generating wizard to go away and generate effectively a 4x4 array patch, very similar to what we have here, but just with a simplified single layer patch. This is one patch on one layer of PCB board stack. Let me just switch off this 3D animation for a moment. Right click, toggle this off, and you can see our board stack on top of one microstrip layer. We have no air gap here. We have no fancy feed transmission line through a slot. This would not give us 5 dB antenna gain in this design per patch, but it is a nice vehicle for me to show you how we run the design. Now in here we have at the top level a circuit diagram that uses the EM structure as a subcircuit. That subcircuit, in fact, that's the wrong one. Let's show you the right one. It's this one here. That EM subcircuit is the 4x4, the 16 array patch that is used as a subcircuit, and we're driving that from microwave office with a real drive signal, in this case plus 40 dBm. The clever thing here is because the two tools were there in the same platform, when we look at the 3D animation pattern of this simulation result, we can right click here, add annotation. And the annotation that we're adding is a planar EM 3D current, field, or annotation pattern. So those allow us to add, as you can see here, pre-simulated the antenna radiation pattern off from the board at circuit level drive conditions. Now that's critical because at the circuit level, we're controlling the phase into each of these elements. So each of these elements here is a control phase block, and we're controlling it by the X and Y position of that particular block. So there are 16 blocks in the design. We're controlling the X, Y position in terms of the phase, theta and phi. And what that means is we can, in simulation, not synthesize the performance of this antenna, but we can actually simulate and analyze. That's very, very different. The analysis allows us to sweep that beam as I change the values of the phase to each of the antennas, and you can see the side lobe patterns changing, the beam steering in both theta and phi if I spin this around. And we can look at the radiation pattern. As I've mentioned, this is not on a complicated board stack with the focus patch or the air gap. We are not getting 5 dBs, and the overall 4x4 is only giving us 13 dBs antenna gain from this configuration. This is actually a built-in example. Under the file open example, ladies and gentlemen, you can get access to this element in the software as we ship it. The file open example brings up something like 400 plus designs. And if you type in the keyword here, antenna, we have 27 of those. The one that I'm showing on screen now is this patch array antenna as a simple patch, but you'll also find one there that talks about the phase array generator in the systems world and that element, and the phased array F file-based array antenna that we can open and show how those work. The log spiral antenna is also built into the tools that I showed earlier on, as is the standalone patch antenna that I use for optimization. So all of those are in the software already available for you to explore and use to your heart's content. Now, I spoke about that radiation pattern being run in the planar tool. That works very nicely when you've got planar elements, but of course, planar elements treat things like plastic cases as a complete infinite layer of plastic. They can't separate out in 3D the various air plastic package layers. So this is an approximation using the planar axiom tool. Why do we do that? It's fast. The simulation time that you saw for that last design, if I bring that back up, was typically around about 3 minutes on my single laptop with 8 cores. So it's a very, very fast design, even though we're looking at simulating a multi-patch array and looking at steerable beam conditions. What we really want to do is throw that design to the 3D tool. and you simply copy and paste the design. Again, back into the software, what you do is you literally drag and drop this design. It gives you an immediate copy. You right click on the copy, go into set simulator, and you simply then choose from the Axiom Planar tool, the Clarity 3D EM solver. That's it. You'll see that from there, we end up setting a box around the elements. Oops, sorry, I've chosen analyst. I did wonder why it wasn't allowing me to do that. It sets a box around the elements. It would set this up in a 3D tetrahedra solver and give us the results from that. No further changes, no import or export of files. It's very, very simple to drive the 3D tool. And I have a slide for that. It does, of course, take a bit longer to run. Of our 4x4 patch running Clarity as a true 3D solver, you can see the return loss and the transmit losses from the patch array, and a similar radiation pattern. It's just a slightly different graphical interface here. To give you an idea of solve times across multiple cores with all of the layers and all of the surface mount components all resolved down to a very, very fine level in terms of the method of, the FEM solve mesh, we're looking at around about 50-minute simulation time on a 20 gigabyte memory compute farm with 96 cores. I appreciate that's a large number of cores. It can be done on the cloud or on a compute farm, but 50 minutes simulation time for this type of integrated design is really quite impressive. So finally, we wanted to look at increasing that design, improving it, going to our proposed 8x4 array design. You can see on the bottom left-hand corner here, we've extended the hierarchy to include one switch. That switch is shown here on the bottom left corner as a green element off board, but that would allow us to start to cascade these 4x4 arrays. And the beauty of that then is that we can look at radiation patterns of the 32 patch array, either on bore site with its interfering underlying signals underneath the board, or as you can see on the right hand side, if we injected and ran two signals, two individual users on different angles, can we simulate and propose and look at the power radiation from those angles and see that we're getting the expected transmit power. Remember that we now have doubled up the number of patches. We're expecting more than 27 dBs of gain from these antenna arrays. So a very, very powerful way of doing this type of design work ahead of ever producing prototype material, ahead of spending money and getting some results. My final slide for today is to look at taking that design and then using that inside VSS, the Visual System Simulator, not testing with a simple CW signal, but in this case, replacing the source with the new radio 5G transmit tone. We can either use a behavioral model for the radiation patterns that I have here, this phase array F element, but look at steering that beam and look at the overall behavior of the transmit and receive chain. Unfortunately, if you look at the spectrum on the right-hand side with the mask in blue, our pink transmit and receive signals are showing that we are out of specification on this link. What I've completely ignored is any type of filtering on the design to enable us to ensure we stay within specification of the band. This is where, so we had an earlier question on data rate. This is where it does become important to include data rate and modulation bandwidth in the system simulation tool. So I hope that answers that question too. Just quickly as a complete plug for our training schemes, a lot of what I've provided today is available as free online training on the Cadence support website. We have over 130,000 customers a year go through this site and look at the training material. We have short training bite videos. When I share the PDF of this presentation, the QR code will take you straight there. We do run blended or live presenter training. I will be in Turkey in a few weeks' time with some of the customers there doing exactly that. And just again, a very quick plug for the European Microwave Show in 2 weeks. If any of you on the attendee list today are attending, please do go and see our teams in Utrecht to ask any questions that you might have there. I realize that I've spoken a lot today. We've gone through a complete design from single patch, demonstrated a very simple one, but explained on this design how we can use quite a clever board stack of material, including air gap and slot line feeds to get our single patch gain requirements, and we've taken that from the budget analysis through to a PCB board layout through to full EM analysis. I've shown you quite quickly how that single patch can be optimized for bandwidth and gain, and we can of course include the PCB height of the air gap, or perhaps even material, the feed line width, the slot gap in that optimization. There is inside the project tab on the left-hand column of the tools a phase array wizard under the wizards branch that allows you to synthesize the ideal arrangement of your antenna design, not just on grid, but circular or on a random pattern if you propose, not of just a square patch, but of the patch that you're proposing. I showed that with the log spiral being replicated multiple times, and allow you to synthesize the performance. But ultimately, we need to export that into the software suite and analyze it with analysis. I've shown Clarity or Analyst, the 3D EM tools that allow us to then look at the beam patterns and even live steering on the electronics. I was showing you it with a tuning tool, but you can do that with SWEP variables to cover all possible phase angles. And ultimately, of course, from that PCB design, we can export this into the production world through Gerber DXF masks. Just to show you quickly, I had got that full design in the software platform. Here is the 3D structure for the EM patch, all optimized for the feed line and the two patches with the air gap above, and the design that was used to do that with the parameterized shape modifiers. This is all in one single project within mmWave Office. We have taken those designs, we've arrayed them across, we've added the surface mount components to make sure that we've got those amplifier chips and the electronic steering control chip. We can view those in 2 or 3D for looking at those elements and how they're grounded. This is part of the bottom of the board for one segment for 4 patches. And we've even taken that design and arrayed it across, not just for effectively the patch that you saw in the visuals, the 4x4 that does solve our radiation problems and get us to the required transmit gain, but also in this same project we have the 4x8 wave patch, and that was simulated and solved in Clarity. I certainly won't do this live on the webinar. It takes around about 50 minutes, but that was looking at the feed that we sent as an ideal 4x8 patch array into the Clarity tool, all in one project. So I'd certainly like to thank you for your attention today. We've got a few minutes left of this hour, and I'm going to try my best to run through some of the questions. I don't know if we can open up the audio at all, Neslian, Mert, or whether that's possible, but I'll just run through some of the questions quickly and answer the best I can. I'd like to thank you for your attention. We will share the slide deck. Please stay for the questions if you wish. Any that we don't answer, if you have provided your name, we will answer via email instead and make sure that we follow those up too. So thank you once again for your time today. I hope it's been a useful presentation. Once again, we will share those slides and we can look at providing the answers. So I think, Mert, you certainly answered the questions. Can we please share the slide deck? Yes, we certainly can. They will come out as PDF soon after we've completed today. What would be the acceptable range for RSSI values? It's very dependent upon the antenna configuration that you're proposing, on your budget analysis that you've got for the chain, and what you're hoping to achieve, be it bandwidth of the signal or perhaps transmission frequency. You can, of course, get much longer distances over a much narrower bandwidth, perhaps, or maybe perhaps with a higher gain antenna. Of course, if you look at SATCOMs, we have very large parabolic dishes that are used for very large gains of single frequency signals. We spoke a bit about the data rate, so thank you for that question. It really comes into play when you're looking at the VSS, the Visual System Simulator side of driving with some real test signals, modulated bandwidth signals. That's very possible to do. You are in complete control of the sampling rate in the system tool. It's a sample time domain engine, but also on the data rate and the modulation bandwidth that we have there. What is the recommended amplification level for the line amplifier? That depends very much upon the manufacturer's devices. Can you get away with, as I did in this case, a single gallium nitride device from Corvo, was giving us the required gain for a single amplifier stage, but you might need a preamp and a high power amplifier. Typically, they might be in different materials, so perhaps a gallium arsenide preamplifier and a gallium nitride for the high power end. It's important to look at output amplifier saturation and that you're not distorting the signals. That would all be shown in the VSS, Visual System Simulator tool, if you're running a nonlinear model for the device. In fact, Modeletics provide libraries for nonlinear models from a lot of the manufacturers today, and they do distort. They do give us distortion products and spurious spectral regrowth because of that distortion. We even have a measurement within inside VSS that allows you to look at cascaded gain headroom. So it allows you to make sure you have enough space above the amplifier levels. The actual basis ratio designed in terms of antenna polarization. Yes, there are built-in antenna measurements. Back inside the software, when we're looking at the graphs themselves, if we were to come into a graph, right-click and add a measurement. In this case, I'm just going to modify this measurement. There are antenna measurement profiles already there. That includes left-hand, right-hand circular polarizations, full transmit power. We can look at swept phi, swept theta, and in critically, the antenna measurements under circuit drive conditions. So you remember with that patch array, I was driving from a circuit level signal. It's important to plot those with a given circuit drive level. So that's quite critical there too. A couple of final questions. In the antenna simulation, does the phased array calculator consider or calculate the mutual coupling between the antenna patches? Yes, it certainly does. I don't know if you spotted, again, I'll try and do this very quickly. In the phased array antenna design itself, when we come into a multiple patch array, we group those antenna patches. And what we do is we start to group them. If I do a 4x4 and look at the element groups, I wonder if I can show you that here very easily. I don't think I can until I auto group them. Let's see. There we go. You can see that what it's doing is it's finding those that are at the corner and treating those uniquely. It's finding those that are along an edge. These are dark green and treating those as a pair of antennas and the way that they operate. And it's finding those towards the center of the array. It does this all automatically. And the inter-element coupling is included in the synthesis. And again, let's go into that element group and auto color. You can see how it's treating all of those in the center there of this 64 patch array as purple, treating them the same in terms of coupling and radiation of elements around them. So yes, it does, but it is critical to include post-analysis, not synthesis, but post-analysis. Can we get to infinite arrays? That becomes a very difficult problem to solve. There are Rotman lenses and Floquet ports that we can propose. At the moment, I don't think Clarity has those, but we are working on that. So thank you very much for that question. Can we arrange to have a meeting at the Cadence European Microwave Show? Thank you very much for that question. Yes, most definitely. Please do speak to Active Nessa. They will be in touch with our channel partner manager, a gentleman called Cam Kashmiri. He will help set up a meeting at the European Microwave Show. Thank you for that one. And to Secular, thank you very much to those that have attended today. I hope it's been a useful presentation. I look forward to hearing more from you in the future. Thank you once again.
Thank you Andy. Katılım gösteren herkese çok teşekkür ederiz. Umarım faydalı olmuştur sizler için. Muhtemelen sizlere ulaşmıştır ama bilginiz için 30 Eylül'de İstanbul'da, 1 Ekim'de de Ankara'da canlı seminer olacak Cadence'ın. Eğer davetiye size ulaşmadıysa bizlerle iletişime geçerek katılım kaydınızı yapabilirsiniz. Onun dışında European Microwave'e gitmek isterseniz, orada görüşmek isterseniz gene bildirebilirsiniz, toplantı ayarlarız. Herhangi bir sorunuz olursa ya da yazılımı denemek isterseniz, demo lisans almak isterseniz de yine bizle lütfen bağlantıya geçin. Çok teşekkür ederiz. Thank you very much to everybody and have a nice day.
Thank you very much. I hope to see you in 3 weeks if you're able to join us at that seminar. Thank you, Neslihan. Thank you, Mert and the Active
Thank
Nessa
you.
team. Pleasure to meet you all. Bye-bye.
Bye.
Thank you, Andy. Bye bye.